All right, class, welcome into week 10. This is the lecture portion of it. So let's click on our course here, and we will go through the things we have seen 10 weeks in a row now. And man, is it slow loading here. But anyway, so one of the things, actually, let me hop back and let it, load up again. One of the things I'm loving seeing, so I haven't gotten to all the discussion boards yet, but look at all this on the side. You people have been busy. Thank you very much. It will pay off in a big, big way, especially because after tonight, you have a week off, a spring break. Perfect time to catch up on stuff if you might be behind, but also just a good way to, break up this semester here. When we come back from it, we'll only have, 5-6 classes left, and we're going to be wrapping things up really shortly here. So if you haven't been keeping up with the discussion boards and the CK12 work, use this time to get caught up, because otherwise, we're looking at less than 40 school days left in the semester for the regular high school I teach at, and then only 6 class meetings left between you and me through the airwaves here. But anyway, so let's hop into it. Hopefully it won't take as long to load up. It's taking just as long. Wonderful. But anyway, so this is our typical screen here, all the stuff here. Make sure you're staying engaged and at least communicating with me. And some of you have done wonderful things with that. I was going to say have done wonderfully with that, but you have done wonderfully with communicating with me, and I appreciate it. It's great because if I have district admin contacting me, being like, "Hey, is such and such participating?" Even if you haven't done a lot of the work, if you have communicated with me, I could tell them they haven't done all the work yet, but they are communicating with me. They're getting it done. They're good to go, and so that way, no dropping, no nothing like that. Anywho, so if we scroll to the bottom here, let me move this out of the way. It's always in the way for some reason. We have our week 10 module. So I'm going to click on that week 10 module, and I'm going to make it public right before your very eyes. Now it's good to go. So at this point, we are used to this cycle now. Discussion board, link to CK12. Actually, I'm going to move that around while we're watching. You get to see all the magic happen here. This is great. So I put the CK12 link at the end simply because that should kind of be the last thing you hop to, unless for 2 reasons. Unless you're just this is way too easy, and I can get the stuff on CK12 done without having to watch my lecture and go through the presentation. If that's you, cool. That's one of the cool things with CK12. All the extra stuff that it has there, the articles, the real life examples, the videos, the study guides, those can all get you through the unit. Now the lecture and the presentation, that's meant to bolster your understanding and sort of talk about what you can be seeing in the unit. So with that being said, we have our discussion board here. We are getting into Metamorphic Rocks this week. We are finishing up our rock families. And then when we come back from spring break, we're going to get to dive into plate tectonics, which is a lot of fun, for me anyway. I only said the one reason. So the other reason maybe you're only doing the CK12 stuff is maybe you just detest these videos and you can't stand to look at my face, in which case I understand. That's not a problem. But just, make sure you're staying up with it, whether it be through the presentations or just the CK12 work or through a combination of both. Please make sure you're staying on top of it. So yes, into Metamorphic Rocks. So the reason we put this unit, geez, I'm getting emails in here. Let me get that away. So the reason we are ending with Metamorphic Rocks is because pretty much every other rock type can be transformed into a metamorphic rock in some way. And then we're going to look at that. And so we put this at the end here. We started with the igneous rocks because we called those the parent rock or protolith, which is one of your questions right there. I didn't give you the answer. But anyway, so we started with those ones because it's kind of like the parent rock. It's where things sort of start out. And then we went into sedimentary rocks because that makes sense as things break down. And now we're going to look into metamorphic rocks, which is how rocks change or metamorphose through 2 key forces there. And you're going to see that in the video. I can't give away the whole thing, otherwise you're not going to watch the video. And look at just the tagline for this video. There's different rocks, and a couple of them have one has a bow tie, one has sunglasses on. I mean, you're going to want to watch that. You won't believe the drama that goes down between these rocks. It is unbelievable. Yeah, so I'm sorry. I'm just trying to get you interested. You know how hard it is to get people interested in rocks? But anyway, Let me hop back. So there's your discussion board. It is required. I do want you to do those. We use those as primers. It gets your brain thinking about what you're going to be seeing and hearing, and also gives you tidbits of information to not only help with the CK12 work and the quizzes, but also connecting to everything that we've done before. We don't want to think of there not being like a flow to this class. There's definitely a flow to it. And now that we are wrapping up rocks and going into plate tectonics, this is a good way to jump off into that. So that video is very important. Not only that, it's graded and it's 10% of your grade. So don't sleep on it. Alrighty, so this link or this click here, if you go to it, it's going to be this right now. So we have a little bit of an inception thing going on. But then also, my goodness, geez, I'm getting a whole bunch of emails here. But then we have the Metamorphic Rocks presentation, which I'm going to get to right now. But I want to first take you on over to CK12, and we can open up our unit for the week. So if I go into my classes, one of the things that I am enjoying seeing is that there is more and more work being done. Even if we go to igneous rocks, not a ton of people, but we're at like 50%. So, that's 50% of the class anyway. Now, this doesn't look at it because it's a 34%, but some people are no longer active in the class, and so that would be the reason. But then when we hop over to sedimentary rocks here, shame, only 6 of you. A lot of you are going to be busy over spring break, taking those laptops down to all those vacation spots, and yeah, everybody's going to be partying. You're going to be hammering away at sedimentary rocks. Shame. No shame. Just make sure you're getting on it because we don't have a lot of time left. But so if we go into our assignments here, Metamorphic Rocks, I'm about to assign this to you right now, and I'm going to set the due date as the week after we come back from spring break, April 1st, which is April Fool's Day. But I ain't joking with you. I'm being serious. You got to get this done. I'm sorry. So let's hop into the Metamorphic Rocks one here. If it'll load. And you're going to like this. Check it out. Oh, wait a minute. Where's my quiz on that one? For some reason, it didn't save the quiz, but I'm going to have to go in there and I'll get the quiz going. Don't worry about it. But so you only have two sections. It's just the metamorphic rocks and then the classifications of it. Mainly because these metamorphic rocks involve just taking igneous or sedimentary rocks or even metamorphic rocks and just applying heat and pressure to change them in some way, shape, or form, which we're going to get to. So that's why there's only two sections there. So it should go really quick, even more of an incentive to get to the other, units that you may have missed. They're all, and there will be a quiz on here, so please make sure you are doing the quiz as well. So that's your CK12 stuff. We know this by now. It should be pretty natural to us, the flow of the class. Let me hop back to the presentation, and I can start to jibber jabber away. I'm going to take a drink of water real quick, and I apologize for being so hoarse at the moment. Okay, so metamorphic rocks. These are rocks that are formed by heat and pressure, and they will sometimes partially melt, but they will never completely melt. And so I'm going to go into full screen here so we can see the whole shebang. And so metamorphic rocks are formed by two types of metamorphism. So we have regional metamorphism, which that type of metamorphism pretty much comes from pressure, and we're going to see where that pressure is derived from. But then also there's contact metamorphism, which mostly involves heat, and that's from an intruding magma body. I encourage all of you right now, Google Iceland earthquake swarm, because they are going to be having an eruption sometime soon. They don't know when, but they've been having like thousands of earthquakes. I'm talking like thousands daily. And it's this magma body on the move that's rumbling the world and shaking the people up in Iceland. And so you're going to have some instances there where there's going to be contact metamorphism because you have this huge hot magma body making its way through the crust, getting ready to become lava on the surface of the earth, and it should be an incredible thing. So metamorphism by pressure. So when we think about what causes enough pressure to metamorphose miles of rocks, we're talking big areas here. And that's why it's called regional metamorphism. So it's like a whole region that's being metamorphosed. And so when we think like what could possibly do all that? And it's just the pressure. And so this is something we're going to see and build on in the next unit with plate tectonics, is the constant moving around and motion of tectonic plates and the tectonic forces can cause regional metamorphism by pressure, just by simply squeezing. And when something is squeezed, it's heated up. And so that can cause change as well. And we're going to see how that can even make mineral grains like line up into bands. And if you're not up on your geology, you might see a metamorphic rock with banding and be like, oh, I can see the layers. That's a sedimentary rock. And you're going to look like a fool, because it's not a sedimentary rock, because you didn't listen to the metamorphism lecture. And I don't want that to happen to anybody. I'm joking. You're never going to be in that situation. You won't look like a fool ever because you're watching this and you're going to be fully up to date. My goodness, I need to stop with all that. So if we take like an original rock, so we're saying quartz grains here. So let's think if we just had a sandstone. So if we had a sandstone and we applied pressure, and so here it says original quartz grains. And so if pressure is applied and enough pressure is applied, the grains will deform and by what's called slippage along planes within the crystalline structure. So the crystal structure of the quartz grains, it gets deformed by this slippage. And then grains can also be distorted. And this gets into some chemistry because ions move from more stressed areas to less stressed areas. And it's almost like when we think of wind. So wind is just movement of air via different pressure systems. So wherever the pressure is being applied, these ions will move around to find a less stressed area as opposed to the area with more stress, and that can cause metamorphism, just a shape change or a structure change via pressure. And so here's a great example of it. So causes a flattening of mineral crystals. So you have this pressure pushing down, and maybe it's these tectonic plates coming together, or maybe they're being pulled apart, or maybe there's material being stacked upon other material. And this is where you should also really watch that video, because they talk about how this happens. But so you have this pressure pushing down, and it will flatten out the mineral grains, and they almost get this flat little structure going. And we have a name for it, which we're going to hop into pretty soon here. So the metamorphism by pressure. So the pressure often causes the realignment of inner-grown mineral crystals. So they will heat up, partially melt, and then like realign themselves. And so this is called, we can call it banding or foliation. So foliation and banding, we'll get into both, but you can kind of see how they're similar but different. So a full-on band is different than something just being foliated. So there's a perfect example of banding. So you can see like these dark and light areas, which are just different, types of mineral clusters there, just forming these nice bands that go through the rock. And we'll get into the names of all these, but that's a great example of banding. And here's an example of foliation. So you can see to where this was very clear bands within the rock itself, the foliation part is not as obvious because it's not as like smooth banded. Sometimes that's a difference in mineral chemistry. Sometimes it's a difference in the pressure being applied or how much pressure is applied. But so those are different sort of ways that we can have metamorphism by pressure, banding and foliation. And so there's a little bit of a closer look on foliation to where you can see like it's been flattened out and there's definite like layers, but it's not like it was with the banding where you can just totally see almost like flows of the mineral crystals through it. These ones have been obviously metamorphosed, but it's more foliated into almost like layers of this material as opposed to bands. And so here's how it can happen. So this regional metamorphism is usually associated with mountain building activity. And when we get into plate tectonics, we will discuss converging plates. That's plates coming together. So these huge bodies of rock pushing themselves together, like you can see in the visual right here. And so if you have pressure on both sides, you can have like mountain building, which is called orogeny. And this is over large areas. So it's not like a small little area forming like a mountain. Like if you look north and you see the San Gabriels, that's an area that's formed via pressure. You have two plates that are sort of like pushing and grinding against each other, in such a sense that it pushes that whole region, up. And you can find a ton of metamorphic rocks up in the San Gabriels, including like schist, gneiss. There's a shale up in there, and you can find a bunch of different types in that area. And so that's how it's formed. Just that pressure coming together will heat up the rocks, will move around the mineral grains, and get them to realign in one way or another. And so this is really large-scale metamorphism. It doesn't occur over like a small little spot. This is like over, many, many miles. Just think of the mountains that we have over by us. Think of like mountains like the Sierra Nevadas or the Himalayas and stuff like that. So it's over very large areas. And you have this sort of what they call confining pressure. So the pressure that is sort of confined to an area. And that's not what we're really looking at here. Now, this can occur, like especially if there's like a dry lake bed, you can have the increasing confining pressure sort of like building up on it. But also one of the things that we're looking for here, once this becomes sort of, we'll say lithified and turned into a rock, if you have this pressure coming in from each side, it just sort of mushes it up and it like heats it and it stresses it out. And you have this, what's called differential stress. And the rock itself gets changed, it gets metamorphosed. And so we take this undeformed strata, we put pressure on it from all different ways, and we get a new type of rock, a metamorphosed rock. Because when we think of metamorphism, it's just a change. And now we also want to look at metamorphism by heat. And this is also called contact metamorphism. We're going to see why. And so what happens here, so this is thermal metamorphism. It's being metamorphosed, strictly by the heat. It's not really dependent on the pressure as much as regional metamorphism is. That's where there's, pressure coming in. This is more like cooking the rocks, like slowly melting them down by what we call igneous intrusions. So this could be like a magma body that is intruding into an area. So if you think of this as Iceland right now, there's these little Icelanders, hanging out on the surface, and just below, like the magma body in the Iceland incident going on right now is only a kilometer below the surface. So that's super, super close. And so as this this magma body moves into the host rock, this unaltered rock, everywhere that it sort of touches and sort of pushes up against, it kind of gets like baked. Just like, if you have like a pot of something that you're cooking, whether it be like water or, ramen, I don't know, anything that's in there that's delicious. If you put your hands on it, like on the pot, obviously you're going to, burn your hands. And it's almost the same thing here. Like the rock that's around this magma body is getting baked. It's getting partially melted. The mineral grains are realigning. And so that's contact metamorphism. So the rocks that are in contact with the magma body get altered. And you can find this up in the Sierra Nevadas in what's called a roof pendant, which is actually like the top of a former magma chamber. And it's found at like the highest peaks. So in these highest peaks, they'd be like the top of the magma chamber, and the granitic rocks that are below it was the magma body that metamorphosed the rock above it simply by contact. All right, so we can kind of see it here. So if this is a hot magma body, and this is, I don't know, some city, let's call it Reykjavik, which is in Iceland. So this is Reykjavik, and this is the hot magma body and all the rock around it that is able to sort of influence and heat up and partially melt will experience this contact metamorphism. And so if we have this emplacement of igneous structures, like we talked about like sills and dikes and whatnot, and all of these different intrusive structures, they will, so like around this here, like around this magma body, that will be your contact metamorphism. You can have, volcanic eruptions from here, like I said, with the Iceland deal. You can have fissure eruptions. Iceland has a lot of fissure eruptions because they're right on two tectonic plates, right on the boundary. You can have what are called cinder cones, which you can see if you just drive up the 395. But always in that area, you can find the metamorphic rocks because of the magma activity going on. And not only that, but also you're in like what's called the Eastern California shear zone. So there's a lot of like tectonic movement, which puts a lot of pressure on rocks. And so you have a lot of regional metamorphism, but also a lot of contact metamorphism because of the magma that's not too far below the surface. So the contact metamorphism, you have to have an igneous intrusion, like we saw in the graphic there. And this is where molten rock is forced between existing rocks. We saw in past lectures, it goes to like fissures and weaknesses in rocks, and then it tends to bake part of the existing rock and it metamorphoses it. Metamorphosed, whatever, it changes it. That's all we need to know. So it doesn't occur over huge areas like regional metamorphism. This is more localized to where the magma body is. but it does change the existing rock around it, what's called the host rock. And so we have different degrees of metamorphism. It isn't the same thing all the time, but depending on heat, depending on pressure, you'll have different results, if you will. And so we can see, like, if we just started off with a clay here, and as we go deeper into the earth, and so if we go deeper into the earth, obviously the pressure is going to increase. As the pressure increases, the temperature is going to increase. And so we can see here that we sort of transform, and there's like this little boundary here, but we can go from a clay to a shale, add a little bit more pressure and heat, to a slate, add a little more pressure and heat, to a phyllite, to a schist, and then to a gneiss. And so anything that sort of goes beyond that into this range, the rock is going to fully melt and you've got a magma. It's not going to be necessarily a metamorphic rock. But there are just different degrees of metamorphism. That's the thing to take away from all of this, or this graphic, I should say, not all of this. And so here's like the visualization of it. So as it goes down into the earth, and as there's more pressure, as there's more heat, there's our slate before, and here's like a good little graphic representation of the mineral grains in there. And then as it goes from a slate to a phyllite, we can see how it sort of changes up. We have a little more of a wavy pattern. It's not as like a straight and linear. And as we move into a schist, more things have been partially melted. Mineral grains can line up. So we have a little bit more of it looks like the banding. And then when we move into the gneiss, we see like almost sedimentary like layers of different mineral grains, but it is not a sedimentary rock. Don't think that a gneiss is a sedimentary rock just because it looks like it's banded. That's where the investigation comes into play, because if you took a gneiss to like a geologist, you're like, look at this sedimentary rock, they're gonna laugh you out of the building. Now, why you do that, I don't know. And don't let them laugh you out of the building. Like you're just learning the rocks. Like, who are they? I'm sorry for getting so animated over this hypothetical situation. Whoops, let me click. There we go. So the composition of metamorphic rock is determined by the conditions of the metamorphism, and then the mineralogy of the parent rock, or the original rock, or the proto-lith, if you will. So when you saw that in the discussion board video, we're far enough into the lecture where I could start to talk about that. The proto-lith, so proto kind of mean first or before, and then lith meaning rock. So it's like the original rock. And so the mineralogy of that original rock will affect the composition of a metamorphic rock. And also, like we saw, the conditions of the metamorphism, the heat, the pressure, the variations there will give you a different rock. So there's a lot that goes into it. And so when I say like rocks tell a story, holy moly, do metamorphic rocks tell a story. They tell you the original rock that it came from, and they tell you how much heat there is, or that there was, and how much pressure it was under. That's pretty amazing, just to get from like one hand sample of a rock. It's a neat thing. And so one of the interesting ones is limestone. So in limestone, it's a sedimentary rock. It could be either a chemical rock, or it could be an organic rock. Someone had the perfect way to put it last week. I don't know if I want to repeat it, but it was the absolute perfect way to put it. And I love that, because that will be in my mind for the rest of time, and I'm sure it'll be in her mind the rest of time too. But as we metamorphose limestone, it just turns into marble. And so it goes from smaller crystals in the limestone to larger crystals in the marble. So in this example, the mineral composition stayed exactly the same. The minerals didn't change, just the crystal size did as it moved into a marble. And then so we could take shale and we can metamorphose it into slate. And in this example, the minerals in shale actually change into other minerals during metamorphosis, meaning that they are partially melted. And then we saw from weeks past that different minerals will crystallize at different temperatures. So as some of these minerals get heated up, they will melt, and they will become like a mush, and then they will recrystallize, but different minerals will crystallize at different times. So shale turning into a slate is a perfect example of this, to where the minerals actually change. To where with limestone going into marble as it metamorphosed, the mineral composition was the same, because limestone is just calcium carbonate. And then it stays the same as marble, it's just larger crystals. So metamorphic rocks can exist from several different parent rocks. An example for this is gneiss. So gneiss can form from a sandstone, it can form from a shale, or it can form from a granite. And so you can take these different types of rocks and metamorphose them, and they can come out to be, a gneiss, which would be the same rock for each of those, but it just has a different origin. And so we don't need to worry about getting too much into this classification sheet here, but it is cool to look at, and you can have it in the, whatchamacallit, this presentation without the lecture. So you can use it as a study guide, and you can kind of see here when geologists classify these rocks. And then so I had to take a whole class just on classifying rocks. And sort of graphic organizers like this are worth their weight in gold. And so the first thing that they can look at is the texture, meaning do we have foliation or is there non-foliation? And that automatically sort of, so say if there was foliation, you can get rid of all these rocks down below and you know it's not that. And then say, if you can go further than that and say, is there mineral alignment or is there banding? And then it goes into grain size, composition, the type of metamorphism, and then finally that will give you like the rock name. And then on the side here is some of the map symbols that you would see on a geologic map. So if you ever see one of those and you see some of these symbols, you would know what kind of rock you're looking at, which is pretty cool. And so all these different characteristics, all these different traits that it might have are used to identify what type of rock it is, which is really cool. Because with the non-foliated ones, you can have coal, you can have what are called the hornfells with quartzites, or the marbles, or the metaconglomerates. And those ones won't display any foliation, so they are a little bit easier to identify. And the ones that are foliated, we just sort of go through the cycle of determining the classification of it. And it can be a pretty fun exercise. And so you can take this chart out with you, like on a hike, and you can determine some of the rocks that you are seeing on your hike. It's pretty cool. It's a neat thing to do. So these are just typical questions. See, these are some of the things you're going to see on your CK12 stuff. So when it says when sandstone is subjected to heat or pressure, it becomes what? And so when we look at some of this, we can go forward and we can look at some of the charts, and you will see some of the charts in your CK12 work. But a sandstone can just become called a quartzite. So let me hop back here because we'll see it there. So there we go. Metamorphism of quartz sandstone will become a quartzite. And that's all it's doing. It's changing from a sandstone to a quartzite based off of the heat and pressure. So is marble a foliated or non-foliated metamorphic rock? Well, if you have this up while you're going through that, then the Metamorphic Rocks classification, which is part of your CK12 work, you would say, okay, marble, let's find it. Here it is. Let me trace it back. Non-foliated. Boom. Done. Question answered. Not too bad. Name 3 minerals in schist. That's a dangerous one. That's a dangerous one. Just don't forget that CH in there. So if you're looking for the minerals in schist, you find schist, you pop on back. It says mica crystals. Okay, cool. Feldspars, right on. And you're looking at the composition over here. You can also have it from this area right here. So mica, quartz, feldspars, amphiboles, garnets, pyroxenes. Those are all possible parts of a schist. All right, and then what is the only metamorphic rock in your, you don't have the ESRT, so we're not gonna worry about that one. That would be more if we were in person and able to sort of look at some other graphic organizers for some of these rocks. So one of the ways to identify it is this handy dandy little chart. Do the rocks have interlocking crystals? No. Okay, then it's a sedimentary rock. That's just like the quick and the dirty of it. If it does have those interlocking crystals like we saw in some of those graphics, it could be either igneous or metamorphic. Then if it's igneous or metamorphic, we can go further and say, okay, is there banding or foliation? If there's none, like when we see like a typical granite, there's no banding, there's no foliation, but there is interlocking crystals. Therefore, it must be an igneous rock. Now, you can also look at it and say, okay, well, there is banding and foliation. Okay, well, then that means it's a metamorphic. And so this is a way for us to sort of classify each of these rocks, determine what each of these rocks are, which gives us a lot of information about where they came from, the geologic setting they were in, and what they've been through, what they've experienced in their lives, if you will. Oops, I always do that. All right. So we're sort of putting a little cherry on the sundae of the rocks in the rock cycle here. So this part I'm going to go pretty quick through because we've seen it before. So all rocks are classified on the basics of how they were formed. So sedimentary rocks form from bits and pieces of existing rock. Igneous rocks form from molten minerals, magma or lava, and then metamorphic rocks form from existing rocks that are changed by heat and or pressure into new ones. And so the rock cycle, we know this. So nearly all rocks are formed from other rocks. There are exceptions, which is like coal, fossilized limestone, and then some of these rocks will exist for thousands to billions of years before undergoing any sort of change. So it's not like this happens like that. Sometimes it could take billions of years in order for a rock to metamorphose. We've seen the rock cycle here. This is just a way that we can sort of get to any other type of rock from any type of rock that we want to start with. But we're familiar with this. I'm not going to spend too much time with it, but you may want to use it as a study guide for your CK12 work. And so this is where we can kind of see all of it coming together. So we can have this melt down here. Maybe this crystallizes down below and it becomes an igneous intrusive rock, a plutonic rock, or it'll erupt through the volcano, cool on the surface really quickly, and it'll become an extrusive volcanic rock. And then from there, those igneous rocks will be weathered and eroded, broken down, transported via, whether it's water, ice, wind. They'll get deposited. They will undergo heat and pressure. They'll become a sedimentary rock. And then with more heat and pressure or anywhere near a magmatic body, they will become metamorphic rocks through the heat and the change. So that's that. You can kind of see here how all of it sort of ties together. And we've now sort of laid the foundation for us to hop into some of the more dynamic Earth processes, like plate tectonics and earthquakes. And then, so we're going to hammer those when we come back from break. And then we're going to talk a little bit about weather. And then we're going to put a little cap on this school year. And thank you for tuning in. And stay safe.